great. So we will start in a minute. Okay, dear friends, I'm glad to start our today's talk. Our speaker is Gaiane Panina from St. Petersburg, Steklov Institute and University, and she will tell us about the new proof, a new proof of Milnor-Wood inequality and beyond. Let's welcome.
Thank you so much. It's a pleasure to be at your seminar. And I expect that I hope that I will tell you something interesting and also very simple, which comes from low-dimensional topology. So please feel free to ask questions, especially at the beginning if you don't understand anything. So there are many co-authors of this work, and let me explain that all of them except Ilya Alexeyev are the students of our faculty of mathematics and computer science at St. Petersburg. And Milnor-Wood inequality part was done with Timur Shamazov and Maxim Turevsky. And beyond is done by me with collaboration with Ilya and Ivan. And these are my students. I'm very happy that we worked together, so it was a pleasure to work with them. Okay. And let me start with very basic definitions. Sorry, I don't understand what's going on. So by some reasons, I draw and my drawings disappear. So let me try it again. So I draw a line and goodness, I checked it worked well. Okay, so let us start with definitions. We are going to work with circle bundles. Now I am confused. I am very much confused. I have some technical problem. Can I please? So I have some technical problems, so I will unplug one of my connections and plug it back. Mm-hmm.
Excuse me, may I help you? What do you need?
I need to quit from the call.
In progress.
So I did something wrong. So just a minute. So I know what should I do. And
Okay.
this is what I'm doing. I am connecting two devices. One is, okay, just wait a little bit. Okay. This way. Mm-hmm. Okay, so this is very strange, but I'm using my my other device and it doesn't show slides. This is very strange. Okay, well, let us do without using only one device. Okay. There will be just one, and I will use okay, just a moment. Now I cannot make comments. It's again very strange. Please, well, so I am co-host at which one of my accounts? Please give me the
yes,
right
I have give you the co-host to your two devices.
my unique. Okay. So let me try again.
Okay.
Okay, I'm here.
Yes, we can see.
Now can I comment? Aha, and now I can comment. Fine. Unfortunately, I cannot comment it. Oh, let me try also. Maybe I can do it here. Oh, now it works. Thank you very much. Okay. Now it works, and I think that I can draw here. Oh, fine. And everything is visible. Thank you very much. So now I'm ready. So let's start with basic definitions. We will work with circle bundles over a very simple object, which are orientable closed surfaces. So these are just spheres with handles. So we are looking at circle bundles whose bases are spheres with handles. And the index sub-index G corresponds to the number of handles, as everybody knows. And we have a circle bundle over this base. And the circle bundle means that for each point X sitting on my base, so the base is SG, and the preimage of each point X is just an oriented circle, an oriented circle. So you see the picture, or the circle looks like a rectangle, but it is a circle. Okay, now let me give you a simplest example of such a bundle. Assume you have your surface SG, you multiply it by S1, which is the circle, and you project it back by the projection, just by forgetful projection, which forgets the second multiple and takes it back to SG. Then what you get is called a trivial bundle over SG, and it is just as it is, very, very simple thing. But trivial bundles do not exhaust all circle bundles over oriented surfaces. And an important thing is that circle bundles over SG are enumerated, are characterized by their Euler classes. Euler class in our setting, so generally it's a cohomology class, but in our setting it's just some integer number. And now let me tell you how, assume you have a trivial circle bundle, which is already understood by us, how to get a non-trivial bundle with non-trivial Euler number. Let us do the following. So let me a little bit, okay, just a moment. Make it a little bit smaller to have more space. So I do the following. This is my surface. And this is a point X sitting on the surface. And assume I have the trivial circle bundle. Now I explain a surgery which turns our circle bundle, our trivial circle bundle, to a non-trivial one. Okay, this looks like this. Let us take a disk in the surface. This is the surface, it's just a part of the surface. And let us take the preimage, this disk, let's call it D, the preimage of the disk, what is it? So the preimage of each point is a circle. Therefore, the preimage of the disk is a solid torus, is some solid torus. And now we do the following. We cut out this solid torus, and therefore, in the total space of the bundle, there arises a toric hole, a hole whose boundary is a torus. And now, what we do, we apply then twist along this direction, then twist. We apply then twist, and we patch the solid torus back in such a way that we get again the closed total space of the circle bundle. And after applying this twist, we get something whose Euler class is 1. And if you want to get a circle bundle whose Euler class is, say, 5, then you have to apply then twist 5 times. So twist it 5 times along this curve. Okay, And actually, this surgery exhausts everything what you can do with circle bundles over surfaces, because dimension here is small, and therefore you can't do too much. And so let's go back to the slides. So circle bundle is this. Its Euler class is some integer number. And an important property is the property number 3, which says that, okay, just a moment. Property number 3. It is unlike vector bundles. Continuous sections of circle bundles exist only in the case when the bundle is trivial, and which is also equivalent to the condition that the Euler number of such bundle vanishes. So if there is a continuous section of the bundle, then the bundle is trivial. And just to remind you, what is a continuous section? So let's go back to our surface. So this is our base SG. For each point X, the pre-image of the point is an oriented circle, and continuous section is just a way of pinpointing one point from each of the circles. So from each of the circle, we take one point, and this cannot be done continuously unless the circle bundle is trivial. Okay, now in order to formulate the Milnor-Wood theorem, the Milnor-Wood theorem is the one at the bottom of the slide. We need the following notion. We need the notion of transverse foliations. Let me explain what is this. Just imagine that we have something like a pack of paper, and I want to fill the total space of the bundle. So we have what we have here. We have the total space. Now our projection pi, and now the base is G. And now we want to express E as the union of leaves. I will draw a two-dimensional picture. So it's very difficult to draw three-dimensional picture. So I will draw SG as a one-dimensional base. So here is the projection pi, and here is the total space E. And we assume that the bundle is circle, so the top is patched, this is the top, is patched to the bottom. Okay, and the foliation is expression of E as the union of leaves. Each leaf is some two-dimensional surface. So in my picture, the leaves are one-dimensional, but in the setting of my talk, the leaves are two-dimensional. And the foliation is called transverse if all the leaves are transverse to the fibers. So these are fibers. So the vertical segments in our setting are the fibers. What are the fibers? They are just pre-images of the points on the base. So all the fibers are circles. So these green guys are the fibers. And leaves are red in my picture. And a foliation is called transverse if the fibers intersect the leaves transversely, exactly as I have depicted. Okay, so it's a very interesting object, the foliation. So let us imagine that you are a person who wants to walk, who stands here on a leaf, and you want to walk around a leaf. And you keep walking around the leaf. So there is some guy walking here. He walks here. And if he walks in the neighborhood of some point, if this guy doesn't go too far, then he would walk around a piece of a section, so around some piece which resembles a section, partial section, over this bounded domain where he walks. But imagine now that, or let me draw it separately, that so there is E, the total space, that this guy walks such a way, makes a loop, which goes around whose projection goes around some handle, and he returns back. And he always keeps staying at one and the same leaf. Then it might happen that when he returns back, not exactly. So the projection would be the same, but he will return using some, he will not return to the same point where he started, because the leaves are not necessarily homeomorphic to the base. They can, so to say, wind around the surface many times. Okay, let us give an example. The simplest example is the following. Okay, let us take the trivial bundle, which is Sg, as you remember, times S1. Then it is foliated. Then it has a transverse foliation by horizontal leaves. And the leaves look like this. They are all equal to Sg times some alpha, where alpha is taken from the circle. No, I'm sorry. I can hear some nonsense. Now it's correct. So what does it mean? It means that, coming back to our pictures, which I already depicted. So we have the base Sg. This is the total space. And the total space is foliated by something which can be viewed as horizontal lines, but in our case, these are horizontal leaves. This is uninteresting. This is very uninteresting, but it is the only example of transverse foliation which is more or less trivial, to say. And it is absolutely unclear that if I give you a circle bundle, and I ask you, can you find a transverse foliation in this circle bundle? Then it's not trivial to find any. And there is a theorem which is quite celebrated one. It's called Milnor-Wood theorem, which says the following. That, okay, so here it is. That an oriented circle bundle has a smooth transverse foliation if and only if the Euler class is not too big. So to say the circle bundle is not too much twisted. So the Euler number can be interpreted as a measure of how much is the bundle twisted. And if it is the Euler number does not exceed the Euler characteristic of the surface, then it is easy to equip, then it's possible, not easy, then it's possible to equip the circle bundle by a smooth transverse foliation. And the examples, the existent type of the theorem are known, and today I will concentrate on this way of that if there is a smooth transverse foliation, then the Euler class satisfies this and that. Okay, and now let me give you a...
Excuse me, a foliation, does it...
Once again?
Excuse me, does a foliation give us a contact structure?
Can we get a contact structure out of a foliation?
Let me tell you.
Do we have a field of planes? Do we have the field of planes out of a foliation?
I tell you, the simple answer is no, but a more advanced answer is yes. The more advanced answer is yes. First of all, foliation is something which is completely opposite contact structure. because of course it gives you a field of planes which are tangent to the leaves, and it is not a contact structure at all. It is something opposite, because the holonomy is always zero, because they are leaves. It can be viewed also, a foliation can be viewed as a connection with zero curvature. So all the holonomies are zero. I mean, all the holonomies which are small are zero. But on the other hand side, there is a similar theorem about contact structures, which sounds exactly the same. So let me say the following. Let me tell how it sounds. An oriented circle bundle has a transverse contact structure. So you just take this foliation and replace by contact structure. Then the Euler class satisfies the same inequality. But today we will
Great.
not. This is interesting because there is an interesting interplay between foliations and contact structures, you know, but it is not, unfortunately, it's really very interesting. But I am not an expert, and today's my today's subject is different. So, but thank you for the question. It is really fascinating property of this up. Sorry.
And who proved the theorem about contact structures?
Who proved? I don't remember exactly. Maybe it was Thurston. Well, all these contact structures and foliations are very dear subjects by William Thurston. Probably he or somebody in his around him. Sorry, I'm not prepared. But
excuse me. So you were talking about surgeries over foliations. Maybe there are some avoidance over foliations. So usually,
I spoke about surgeries over circle bundles. You take a trivial circle bundle, for instance, and you apply this local surgery, and you get a circle bundle with some different Euler class. So this how you can rule the Euler class. Okay. So let me continue. Here is the classical proof of the Milnor-Wood theorem, which I'm not going to tell you in many details, but it is worthy to be mentioned. So this is something which you can see in textbooks. So first observation is that a foliated bundle is related to some group homomorphism from the fundamental group of the base to the orientation preserving homeomorphisms of the circle. And of course, this is a very classical object which was studied by Poincaré. And so there is a way to patch, whenever you have such a homeomorphism, you can patch a circle bundle which will be automatically foliated. And if you know the homeomorphism phi, then you can express the Euler number of the resulting bundle via phi. So you should look at the standard generators of the fundamental groups. You should look at their commutators. You should look the rotation numbers that correspond to their commutators, to their products, and all that stuff. And then you should apply the properties of Poincaré rotation numbers of products and commutators, and then you win. Because you know how to express the Euler number, and there are some bounds. For instance, if you have two elements from here, then the rotation number of their commutator cannot be too big. There are bounds from above. Okay, this is a classical.
So am I right that this is about commutator length? So we are solving something in group theory, and there is something like commutator length.
Well, no. Let me tell you some more details because it is very quick. So what are the standard generators? The standard generators are A1, B1, A2, B2. With each handle, you have two loops. This loop and the other loop, you know, and so on. And therefore, you have AG, BG, because G is the number of the handles. And then you have such a product. And in the fundamental group, there is a unique relation that the product of the commutators AI, BI equals 1. And so I here ranges from 1 to G. And whenever you have a group homeomorphism, you can look at the values of phi on these generators. Then it is no longer 1, but there is a rotation number which belongs to Z. So you need here some definition. So if you are familiar, then it's good. If you are not familiar, just skip this part of explanation. And so this rotation number is exactly the Euler number of the circle bundles. And then you say that this rotation number cannot be too big because there are some bounds. This is how it goes. So let me clean everything and let us go to the next slide.
Is there any chance to get a relation to the braid group on the surface? I think the fundamental group is the braid group on one strand, but is there any chance to get some braid group of more than one strand? Still,
with relationship to which problem? What is the problem?
Well, to the Milnor-Wood theorem.
But we don't need. We need just by one. But probably it's a good idea, but it is good for some other problem. This is what I mean. Okay. Now, here is our idea. So we have a foliated circle bundle. Let me draw it this way. So again, this is SG. This is the total space. And it is somehow foliated. So it goes like this. So there are leaves. There is a transverse foliation. And then what we say? We say, come on, the leaves, they look very much like sections, because you can take a piece of a leaf and it is transverse. The leaves are transverse. They are transverse to the fibers. So let me draw fibers. And when I fix a piece of a leaf, this means that in each fiber I mark a point. So this is a section. This is a section. Therefore, my problem, my circle bundle is just trivial, because existence of a section means triviality. And of course, this is wrong, because as I already explained, if you continue further, you get something like this. So you return back, but not to the same point. And so our idea was to look at a piece of a leaf. So idea is very simple. Take a part of a single leaf, not the entire leaf, which is infinite, probably it's everywhere dense and very ugly, but we just take a part of a single leaf. It looks like a section, but it is not a section. it is something which what we called flat quasi-section, because it resembles somehow sections, but it is not a section. And so what we did before, we developed a generic theory of quasi-sections. And now let me tell you a little bit more about that. So I'll eliminate this all, and I again draw the same picture. This is G. This is the total space E. So everything in between is E. And what is a quasi-section? Quasi-section. I draw something here, which is not necessarily a section, just anything. Probably disconnected, probably with intersections, probably with singularities. The only thing I care about that the projection of this red thing is a quasi-section. And I only care about that its projection covers the entire base. And the idea is the following, that the quasi-sections, they exist always. They exist for any circle bundles, for any. And the problem which we solved together with Timur Shamazov and Maxim Turevsky is the following. Okay, assume you have a quasi-section. How can you retrieve the Euler class of the bundle? And we have an answer. The answer is the following, that you should look at singularities quasi-section. Each singularity should be this is what is written here. Each singularity has its own weight, which there is an effective formula how to compute it. And looking at, and if you sum up all the weights, you get the Euler number. So the Euler number of the circle bundle in terms of quasi-section equals the sum of the weights of all singularities of the quasi-section. And this is very good that we could prove Milnor-Wood theorem using our formula. And let me explain what we do. So here is a definition. A quasi-section is, we take arbitrary surface Q and map it to the total space. And the only thing we care about as the projection is the entire SG. And in our case, we need a very specific quasi-section. Let me explain it now. So we have the universal cover. Sorry, it read. The universal cover of our surface. And we have also the total space. And I take I take SQ, I take a subset of the universal cover. And so I need to map it to the total space. So I need to find this map Q. And I take the map Q, which does the following, which makes the following diagram commute. So we have the projection from the universal cover to our surface, and we have projection here by the projection of the circle bundle. And we wish to satisfy the following. The diagram commutes. And secondly, the image of Q capital should belong to a single leaf. This is exactly what I told you, that was a person, so there's a foliation, and a person walks along a single leaf. And if he has this Q, then this person also gives us a quasi section which belongs to a single leaf. Okay, and so we have something which looks like this. The quasi section is like this red part of one leaf. Okay, and now our idea was to take a very specific I will let me skip 2 slides. They are boring, and this is again this thing I told you. So the Euler number equals the sum of
What is BB?
don't look at BB. These are the weights of the singularities. In our case, the singularities will look very simple. And let me go exactly to our construction. Okay. I will explain it. Don't worry. So, in our case, we assume. Let us assume for simplicity that the number of handles, that G is greater than 1. Then the universal cover of SG is the hyperbolic plane. And this is the standard picture in the hyperbolic plane, which is the universal cover, that let us unfold SG as a regular for G gone. And then we have this standard picture that the universal cover is tiled by fundamental domains, and each fundamental domain is this for G gone. And here in this picture, you see exactly one of these fundamental domains. It is in the universal cover, so it looks like this. It's a hyperbolic polygon, which is regular. Let us think that it is regular. It doesn't matter, but it is, it's nice to think so. Okay, and what is the disk D? What is that Q? What is the disk Q which we put on the leaf and which creates our quasi-section? So we need to find something in the universal cover. And this is the disk which is bounded by this curve. So you see the curve. It is the green curve, and then it is the red curve, and it bounds. It bounds some disk, which looks a little bit like an octopus, but it is a disk. And what we're interested in is the projection of the boundary of this quasi-section. So let me explain once again what do these pictures mean. So this is the universal cover. This is the piece of the universal cover. Tiled.
You're not audible. I can't hear you. I can't hear you. Excuse me.
You can't hear me?
We can hear you. I can hear you.
Is there any problem with?
No, it's okay.
Okay. So let me once again explain what we see in this picture. So here is the universal cover, the piece of the universal cover, one fundamental domain, and the disk, which is like this. And here I depict the unfold of SG. So I cut it along the standard generators and unfold it to the 4G gone, which is basically the same as the fundamental domain. And this, what is depicted here, is the projection of the boundary line of our disk. So you see the green curve. This is the green curve, and this is its projection. And these are projections of the red petals, so to say. You see there are many small red petals and one big green petal, and the other projections. And of course, the projection of the boundary of the disk has many self-intersections. has many self-intersections. All these self-intersections are marked by stars, you see, small stars. These are the singularities. These are the singularities we are interested in. Okay, this is the same picture, but
Excuse me, I don't quite understand what a red curves on the right picture mean.
okay, so you see, it's a. Let us look on which right or left. Okay.
Right, the right one.
Right. Okay. Okay. Let me show you. Let me show you. Let us take this part. You see, I'm drawing it bold. This part of the red line on the left. Okay. And it projects to one of these lines. Maybe not to this one, but one of these red arcs.
Okay, I think I start understanding.
Well, it's a little bit, maybe you shouldn't go that much into details, but if you just sit and think and meditate a little bit how to draw it properly. And of course, probably this picture is a little bit deceiving because in reality, the angles are different, you know, everything is different. Probably this is not convex, probably it goes something like this. This would be more realistic, but I need to pinpoint all the intersection points. This is important. Okay. And so what are these numbers? So you see the numbers 1, 2, 3, and they show how many leaves of our quasi-sections of our quasi-section are in the preimage. So let me give here a little bit more details. So again, this is our standard picture. This is our foliated circle bundle, and this is our quasi-section, which is a piece of a leaf, so it terminates somewhere. Somewhere there is boundary, and whenever you take a point in the base, say this X, you see that in the preimage, it hits the quasi-section only once. So this means that this point is maybe from this domain. And if you take a point here, X, then you see that preimage hits the quasi-section twice. And of course, these numbers, they change exactly where we have self-intersections of the boundary. So you see, it's very low dimensional, quite understandable pictures. And I tell you what happens with the weights of these singularities. So all the singularities, they look one and the same. Let me go to the picture. Okay. So all the singularities we have, they look one and the same. So there is a singularity point X which is the intersection of projections of the boundary of our disk. And in the preimage, you have two sheets with boundary. So you take the point, you take its small neighborhood, and you look at the preimage of the neighborhood, and you have two sheets with the boundary and one sheet without the boundary, the gray one. And according to our formula, which I want, so here is some formula, you just apply it and ignore it because it's boring to explain what all these numbers mean, but only trust me that in our case, each of the singularities contributes either +1/6 or -1/6, according to our formula. Okay, and plus or minus because we don't know about the orientation of the picture we have in the preimage, which plays a role. Okay, and now coming back to our picture. By the way, see, this is a picture which reflects the situation when G equals 2. This is for the sphere with two handles. It is very easy to compute how many are there intersection points of the boundary, and generically for any G there are that many singularities, 3 times for G minus 2. Okay, each of these singularities
And why
contributes.
isn't it attainable? Excuse me. And why is this value not attainable, not achievable?
Not achievable. So just a moment. Wait a moment. First of all, let us understand this. So I haven't finished yet. Each of these singularities contributes either 1/6 or minus 1/6. And we know that the numbers of the ways is the Euler class. So therefore, we just multiply this by 1/6 and we get 2G minus 1. And Milnor-Wood inequality says that there should be 2G minus 2 at most. So we have almost done, but we need to prove that the value 2G minus 1 is not achievable. And here is the proof. It's funny that, well, it's funny, but I'm afraid I cannot explain this. There are many ways to explain why it's not achievable. But I will try. Let me try. Okay. So let's come to singular points. You remember that the fibers are oriented circles. So in the preimage of the neighborhood of a singular point, we have either this picture like this, or its mirror image, which has a different orientation. So in our setting, everything is orientable. The base is orientable, and the fibers are orientable. So this picture has an orientation, and its mirror image has a different orientation. And assume, coming back to our problem, why this value is not achievable? Because if we have this value, then all the singularities should contribute one and the same sign. Say all of them contribute 1/6, or all of them contribute minus 1/6. Okay? And this means that the local pictures like this should be all the same. Should be all the same. I mean, the orientation should be all the same. And this leads us to a contradiction because if you look at the neighborhood of the vertex of our fundamental domain, so all these points, they are one and the same after patching, then you see something which resembles an unexistent world of Maurice Escher. So it's an existing picture which does not extend further, meaning that this disk you can put to the leaf, but its extension, which is a little bit bigger, say embraces that much, is not liftable to a leaf of our foliation. Okay. Oh, just a moment. I will look at time. Yes, I'm almost.
So can you show the slide where n of x and the other number k of x are defined? N of x is the number of regular sheets.
Okay, it's well, if you wish. So there are two numbers, n and k. So what you do, let me do the following. So this is X, which is a singular point. And you go along the fiber, and the fiber has orientation. So I go along the fiber according to its orientation. Okay. Sorry. Okay. So first of all, First of all, I need to put numbering on the bordered sheets. So this is the sheet number 1, this one. And the second bordered sheet is the sheet number 2. Why? Because when I go along this circle, so I start with a point where there are no bordered sheets in the pre-image. So let's say I start here, and I go along the circle, and I look up. So I go this way, and I look up. And the first bordered sheet which I meet is this one. Therefore, this is the sheet number 1. And the other one is the sheet number 2. Okay. Now, now I have an ordering on my bordered sheets. And now, okay, what is K? So now I go along the fiber. Now I go along the fiber, and fiber is a circle. The fiber is a circle, and I have a sheet number 1, which intersects my circle at one point. I have a sheet number 2, which also intersects my fiber in one point. That's fine. And there is also a regular sheet, which is depicted gray. And the regular sheet might sit here and might sit here. And so these two, so it sits either here or here. And these two situations, they differ by orientation. So you see, this is the red circle is a fiber. It is oriented, so there is orientation. So this triple of points is either positively oriented or negatively oriented. And depending on the orientation, you have either 1/6 or -1/6. And in our setting, so N is the number of regular sheets lying between the first and the second border sheets. It should be bordered sheets. If one counts from the first border sheet in the direction of the fiber. So I go from here to here, and how many regular sheets are here? So it is N. And when I go from here to here, I count the number of regular sheets, it is K. But in our case, there is only one regular sheet. So, and there is a typo. So we have K 0 and N equals 1. Sorry very much. There is a typo. And we have that weight. And then you substitute, and then you make simple computations, and then you are done. Sorry, there are many typos in this slide. I apologize. I was not assuming that I go so far. Okay. So okay. Now let me skip, or maybe I tell you the details. So our proof, so to say, it is very simple and short, but it relies to our combinatorial formula, which computes the Euler number by the weights as the sum of the weights of singularities. So the core of our proof is our combinatorial formula, which relates quasi-sections and Euler number. And of course, it is not trivial to prove such and such a formula, but we did it. Okay, and now tell me, please, how we derived this formula. I will tell it very shortly. Okay. Here how it goes. Now let me remind how a way of constructively define the Euler number. Okay, so we have our base. We have our base, and assume we have a circle bundle, and we know already that there is almost never continuous quasi-section. But it is always possible to create I'm sorry, not quasi-section, section. There is a continuous section exists only for trivial circle bundles. For non-trivial circle bundles, it is possible to define, to construct a section which is continuous, but not everywhere defined. So assume we have a continuous section which is defined everywhere except of some finite set of points, like here. Then there is a way to looking at this section, partial section. There is a way to compute the Euler number. It goes like this. Okay, our section is not defined at point xi, but it is defined on the small circle which embraces the point. Okay, it is defined, and therefore in the preimage we have locally trivial bundles, so we can assume that we have our section which is defined here defines a map from this circle to this circle. Our section, its restriction on this circle, small circle, defines a map from the circle to the fiber. It is written here. So we have two oriented circles, because by definition everything we have oriented. So there is a well-defined notion of the degree of the map. One circle maps to another. There is degree of the map. And let us call the index of this point x just the degree of this map. And then the Euler number equals the sum of indices. So the recipe is simple. If your section is not defined at finite number of points, you just for each of these points take the circle, compute the degree, sum up the indices, and what you get is exactly the Euler number. Okay, let's move further. And there is a very beautiful idea by Maxim Kazaryan, which we call Kazaryan's averaging principle, which we used. And it looks like this. Okay, now assume you not have just one section defined outside some finite set of points. Assume you have a finite number of sections, or if you wish, we can speak about a random section. Then, of course, the Euler number equals the expectation of this sum. This is absolutely clear because this expectation is a constant, is a non-random number. It's just constant, which is the Euler, which equals E, the Euler number. And then after that, you can interchange expectation and the sum and write like this. So you have to take the expectation of the index produced by a single point xi, expectation over with respect to your random section, which is very non-trivial now. And well, I mean, this is quite elementary. And we are going to apply this formula for random section with a finite probability space. So in simple words, we are going to just to average. Well, when you have a finite probability space, we speak of averaging for simplicity. That's why it's averaging principle. Okay. And now let's use this simple idea and do the following. Okay, so we have our quasi-section. Let me remind you what it is. So this is the base, SG. Now I draw it two-dimensional. And this is the total space. And this is a piece of total space. And this is a piece of my surface. This is projection phi. And quasi-section is any ugly thing which sits here. Maybe there are faults as I depicted here. Maybe there are singularities, whatever. And now the recipe is the following. Okay, take the projection of the quasi-section here. And then you see something which is called landscape. So these are projections of the faults. There are Whitney umbrellas. There are lines of self-intersections. There are projections of pleats. So whatever exists in the classical singularity theory, you project down and you see something like this. And then you see that the base, so the base, let me draw it here. So the base turns cut into such domains which you see here in the picture. And now the idea is very easy. Okay, let us create a random section. I pick a point here in a domain. I look at the pre-image. I see a number of sheets in the pre-image. For instance, for this point, I see 2 sheets in the pre-image. And over this domain, I take my random section to be equal to one of these sheets with equal probability. And then I average further. So I need further averaging, and this all works. And then you need just to patiently and accurately compute all the weights depending on what type of singularity we have. And then we were done. Then we have the formula, and now we can, and we do, apply this formula in different settings. Okay. Now comes the part and beyond. And beyond, I am not going to, so, okay. And beyond theorem tells us what happens if we look at higher dimensions. Now we go to higher dimensions, and everybody knows that in higher dimensions, things get much more complicated. For instance, we cannot tell what are closed smooth manifolds. There are many problems with them. There are just definitions and nothing else, and some examples. Okay, and here is a theorem which we proved very recently using the same ideas of quasi-section. How does it sound? Assume we have a closed, oriented, smooth manifold, M, n-dimensional, any dimensional, finite dimensional one. And we also assume that its fundamental group is amenable. If you don't know what is amenable group, then you just ignore this part, and you may think, as a simplification, that amenable group is a group with sub-exponential growth. This is not true, but you may imagine something like this. Okay, and then it makes no sense to look at circle bundles, but instead we look at bundles whose fibers are spheres of dimension n-1. So you see that this is a generalization of our setting. In this case, Euler numbers also exist. Well, Euler class exists always, but with these dimensions, it is a number. It's just a number. And the statement is the following. If the total space admits a smooth, transverse, affine foliation, I'm not going to explain what is that, then the Euler number of the bundle vanishes. And the idea of the proof is basically the same. Look at quasi-section, try to apply, so let me do here it is the theorem and here is the proof. So you take a big flat quasi-section, you apply Maxim Kazaryan's averaging principle combined with Dennis Sullivan's trick, and then you are done. And since I have...
And so two questions. So first, why is it 0, but not just 0 and not only estimated? And also, where do you use amenability?
I tell you, this is what I was going to tell. There exists also an estimate, but it is our work in progress. It can be estimated, but we have not written it. It's very recent result. And now where we use amenability, because we are doing something different compared to what I have told. So, okay. So let us take the universal cover of our manifold. It is something huge, but it is also tiled by fundamental domains, and not by squares, as I have depicted, by something ugly, probably, but there are also fundamental domains and tiling of the universal cover by fundamental domains. Now, what we take as Q, so we take a piece of the universal cover and create a finite piece of the universal cover and create a quasi-section. And now we take a piece of the universal cover, which is big, which embraces many fundamental domains related to, so if you know, what are the fundamental domains which we choose here? They are related to Föllner set. Or if you don't know what does it mean, then forget, and just a ball in the calligraph. Then more or less the same idea is applied. So you project it down to, so you have this guy, you raise it to a single leaf, and then you do the same. You do basically the same because, I'm sorry, because
Well, I still don't understand. So your statement is much stronger. You say that the Euler characteristic is 0, and you are saying now that the estimate is a work in progress, but the exact value is already done. So how can it be happen?
no. So
how can it happen?
Okay, sorry. If the fundamental group is amenable, then this is true. But if the fundamental group is not amenable, then we have an estimate.
Okay.
A plus estimate for non-amenable. case. That's it. But it is, well, it is not yet done, so we are working on that. It's a work in progress. And the idea is the same. But the difference is that here we take a very big piece of the fundamental domain. It's no longer disk, so because we don't know what is it, we only have one connectedness, and it works. We're happy, and it is not a new theorem. This theorem follows from Gromov's results and from Gromov, Sullivan, and some other results, but it relies on Nikolai Ivanov's work on bounded cohomologies, on Gromov's norm, on Gromov's simplicial norm, on very nice, very interesting, but quite involved notions. And we did this without that. Okay, so I think I should stop here. Please ask questions if there are any.
Okay, thank you very much for a very nice talk. Are there any questions or comments?
Excuse me, Professor. Can you show your reference about this work?
So about this one.
Is it uploaded to archive?
Yes. This theorem, and the previous one, Milnor Wood. Everything is on the archive, and you just Google, just search for Panina, and you will get it. Yes.
Okay, thank you.
So they are not yet published.
We have a lot of projects. For example, reading papers together, and I will immediately look at me and maybe someone else. Upload video. To make friendship between seminars and many other things. And we would be happy if you can join our channels, discussions, papers, or whatever else. I really appreciate your talk. And we will be reading your paper together with.
The paper about Milnor Wood part, the simple part, it is on the archive, and it will be a chapter in a book. We are already invited to publish a chapter in a book, which is entitled In the Spirit of Thurston. And we tried our best to put in many details, to sketch the proof of this classical proof of Milnor Wood theorem, also sketching a proof of Sullivan's proof of this theorem. And so that there are more examples, better pictures, and so on. And
okay. Yeah.
So, but the last one is not that well written as the Milnor Wood part, because it is indeed a work in progress. So it is written, so we tried our best, but it is hard reading, and Milnor Wood is easy reading. This is what I say.
Okay. And any more questions? Okay, if that's not the case, so let's thank the speaker again.
Thank you very much. It was a pleasure.